Beneath the vast frozen deserts of our planet, where sunlight barely caresses the ice and silence reigns unbroken, lie secrets older than humanity itself. Hidden beneath kilometers of ice, there are lakes untouched for 1 million years, time capsules, preserving a world that has never known our footsteps. Imagine descending into darkness so absolute. The ice above feels like the sky itself, and each breath carries the weight of eternity. These are not merely frozen landscapes. They are gateways to life's ancient whispers, fragile ecosystems waiting to reveal what Earth has long forgotten. In this realm of relentless cold, where every frozen wind whispers stories of isolation and survival, we embark on a journey few have dared to tread. What lurks beneath the ice? What mysteries lie in these sealed waters? Today, we follow paths carved by glaciers and guided by science, venturing into the hidden arteries of the polar frontiers. Before the mysteries unfold fully, remember to like, share, and subscribe to join this journey into the untouched corners of our planet. Beneath the endless white stretches of Antarctica and Greenland, the world feels suspended, caught in a stillness that seems older than time itself. The ice rises like cathedral walls, vast and silent, reflecting the pale, unyielding light of the polar sky. Here, where the wind sculpts invisible paths and the sun barely touches the horizon, the Earth keeps its deepest secrets locked away in liquid darkness. Subglacial lakes, hidden beneath kilometers of frozen ice, are the ultimate time capsules, pockets of water, isolated from the atmosphere and the rhythms of the outside world for millions of years. They exist in a realm that defies human comprehension. Frozen fortresses that cradle ancient life and preserve the echoes of climates long vanished. These lakes were formed in the silence of prehistory, shaped by ice sheets that moved imperceptibly over millennia. Layer by layer, the ice accumulated, pressing downward with immense weight, sealing the water below from the chaos of the world above. Within these sealed waters, the chemical whispers of Earth's past remain intact. Trapped gases, ancient sediments, and microbial life that has evolved in isolation, untouched by the cycles of seasons or the intrusion of humans. Every molecule, every drop, is a messenger from an era before our civilization, holding clues about climates that have risen and fallen, ice sheets that have advanced and retreated, and life that has endured against all odds. Imagine a lake untouched for 1 million years. A world beneath the ice, silent yet teeming with life, yet existing in total darkness. No light penetrates these frozen ceilings, no warmth caresses the water, only the faint pulse of geothermal energy keeping it from freezing entirely. The ice above is both barrier and protector, ensuring that the water beneath remains pristine. In these conditions, life has learned to adapt in ways unimaginable. Microbes drift through the nutrient-starved waters, surviving in isolation, suspended in a world that humans can only imagine through the lens of science and the whispers of theory. The landscapes above these lakes are deceptive. To the casual eye, it is a wasteland of snow and ice, a featureless expanse where the horizon blurs with the sky. But beneath that stark surface lies a network of hidden reservoirs, connected through ancient geological pathways, shaped by the weight and movement of the ice itself. Some lakes stretch for dozens of kilometers, others are smaller, yet each carries the imprints of time, like pages in a frozen book waiting to be read. Scientists have compared them to islands in a sea of ice, isolated sanctuaries where evolution took a different course, untouched by the contamination of the modern world. Reaching these lakes is not merely a matter of digging through ice. It is a confrontation with the extremities of our planet. The ice above is thick, often several kilometers, and the cold is unrelenting, biting, and omnipresent. Every step toward discovery is a battle against the silence, the isolation, and the oppressive white horizon that seems infinite. Yet, for those who dare to probe beneath this frozen canopy, the reward is profound. A glimpse into the Earth's memory, a vision of worlds preserved in ice, a chance to witness life in its most resilient form. These frozen time capsules are more than scientific curiosities. They are mirrors reflecting the fragility and endurance of life. They remind us that even in the harshest environments, nature finds a way. They also serve as warnings, evidence of how our climate has shifted over eons, and how delicate the balance of our world truly is. As we peer into the depths of these lakes, we are also peering into the past, into stories written in water and ice, narratives that predate human history, waiting for those brave enough to uncover them. And yet, the question remains, what will we find when we finally break through this icy ceiling? What forms of life have been quietly thriving, completely cut off from the rest of the planet? And what secrets do these waters hold about the Earth's own history, about the cycles of ice and fire, of survival and extinction, that have shaped the world as we know it? The ice above these hidden lakes is more than a frozen barrier. It is a storyteller, etched with the passage of time. Layers upon layers of snow compacted into ice hold a chronology of the planet's climate, a record of ice ages and warming periods, of storms and calm that predate human memory. Scientists call it an archive, but it is more than that. It is a monument to endurance, a tangible proof of the Earth's patient, relentless evolution. Every crack, every fissure in the ice carries meaning, a language written by the forces of wind, temperature, and pressure. And beneath it, the lakes lie waiting, like silent witnesses to a world that has moved on without them. The isolation of these lakes is absolute. For 1,000,000 years, they have been sealed from rain, snow, sunlight, and wind. No life as we know it has intruded. And yet, paradoxically, life persists. Microorganisms, invisible to the naked eye, survive by extracting energy from minerals in the sediment, from the faint warmth seeping from the Earth's crust, or from chemical reactions that mimic the processes sustaining life in other extreme environments. They are master survivors, living in the shadows of history, teaching us that existence is not bound to the comfort of light and abundance. These organisms have adapted to starvation, darkness, and extreme cold, and their very existence challenges our understanding of what it means to live. The chemistry of these waters is equally extraordinary. Without contact with the atmosphere, oxygen levels are carefully balanced, nutrients are trapped, and the waters often carry unique compositions of salts, minerals, and gases. Each lake is a separate universe, shaped by its geologic and glacial history. Some are rich with ancient carbon, while others hold methane or other compounds that reveal processes hidden from our eyes for millennia. Every drop is a repository of information, a frozen library in liquid form, preserving records of ice sheet movements, atmospheric changes, and even the potential for ancient, unknown life forms. To even begin to explore these lakes is to embrace danger and uncertainty. Scientists have pioneered techniques that allow sterile drilling through kilometers of ice, ensuring that the waters below remain uncontaminated. Every step, every action must be precise. One wrong move, one trace of modern life, could erase the delicate ecosystems preserved for eons. There is a reverence in these expeditions, a quiet acknowledgement that humans are intruders in a world that has existed long before us and will continue to exist long after. It is not conquest, but stewardship, a chance to learn from what has endured in isolation. As the ice melts momentarily beneath the heat of drilling equipment, revealing the first glimpses of water below, there is a tangible sense of awe. Here, in the shadows beneath kilometers of frozen crust, the lake stretches silently, its dark surface shimmering under artificial light. It is both alien and familiar, a reminder that life, in its most tenacious form, will find a way. These waters challenge our assumptions, forcing us to rethink what is possible and what it truly means to survive. And while the lakes may appear lifeless to the eye, teeming life thrives in forms we cannot yet see, waiting for science to uncover its secrets. Beyond the science, there is poetry in the existence of these lakes. They are mirrors of eternity, reflecting not only the conditions of the past but the resilience of life itself. They whisper of patience and persistence, of adaptation and quiet endurance. They remind us that time is not linear but layered, folded into ice and water in the hidden spaces of the planet. And as explorers peer into these depths, they confront more than ancient water. They confront the profound silence of existence, the fragility of life, and the immense scale of geological time. In these frozen chambers, humanity finds both humility and inspiration. Humility, because the lakes are a testament to forces far greater than ourselves. Inspiration, because they reveal that life, no matter how small, can endure the most extreme conditions imaginable. And in that endurance lies a promise that discovery is still possible, that there are worlds untouched, waiting to tell their story, and that the frozen frontiers of our planet are far more alive than they first appear. The formation of these subglacial lakes is a story written over eons, a narrative of ice, pressure, and geological time. Each lake owes its existence to the immense weight of the ice above, which, paradoxically, both crushes and preserves. As snow accumulated over millions of years, it transformed into dense glacial ice, slowly flowing like a frozen river toward lower elevations. In some places, this ice ground into the bedrock, carving valleys and depressions. In others, it created pockets where water could collect, insulated from the frigid world above. Over time, these pockets became lakes, sealed from the atmosphere and protected by the very ice that threatened to freeze them solid. Geothermal heat from the Earth's interior plays a subtle but critical role. It seeps through the rock beneath, preventing the lakes from freezing completely, creating a delicate balance that has persisted for millennia. It is a dance of forces: ice pressing from above, heat rising from below, and water trapped in between, suspended in perfect equilibrium. This balance is fragile, yet it has endured longer than any human civilization, longer than the oldest written record, a reminder of the immense scale of geological processes. As scientists study these lakes, they are also confronted with the echoes of past climates. Sediments at the lake beds are more than inert material. They are pages of history, recording atmospheric changes, volcanic eruptions, and glacial advances and retreats. Every particle tells a story: microscopic pollen from forests long gone, chemical signatures of ancient oceans, traces of life forms that thrived in eras when the Earth was warmer or colder. To peer into these sediments is to peer into time itself, to witness epochs unfold silently beneath the ice. Isolation has also fostered evolution in the most extraordinary ways. Microbial life in these lakes has adapted to darkness, extreme pressure, and scarcity of nutrients. Some species metabolize chemicals in ways unfamiliar to surface ecosystems, surviving by extracting energy from compounds locked in sediments for millions of years. These organisms are not relics. They are innovators, shaping and reshaping their tiny ecosystems without ever seeing sunlight. In their quiet persistence, they offer a glimpse into the potential of life beyond Earth, hinting at possibilities in environments as extreme as Jupiter's icy moons or Mars' underground reservoirs. Exploring these lakes requires not only technology but patience and precision. Scientists employ sterile drills, robotic samplers, and advanced sensors to prevent contamination. A single misstep could introduce foreign microbes, obliterating the natural balance preserved for millennia. It is a humbling reminder that in the realm of the polar frontiers, human ambition must yield to caution and respect. And yet, the reward is profound. Even the faintest signals of life, the smallest chemical traces, can rewrite our understanding of biology and survival. Above the ice, the polar landscape remains a stark contrast to the hidden life below. Endless white plains stretch to the horizon, punctuated by jagged peaks and hidden crevasses. Wind sweeps across the surface with a force that can strip flesh from bone, and temperatures plummet to extremes that defy imagination. It is a land where survival is a daily struggle, where even the hardiest explorers are dwarfed by the scale of nature. Yet, it is this very extremity that preserves the lakes beneath, a paradox where danger and discovery coexist, where the very elements that challenge life above ensure the persistence of life below. The frozen time capsules challenge our perception of isolation. We often think of solitude as emptiness, but in these lakes, isolation is life-sustaining. Separated from external disturbances, the water remains pure. The organisms within continue their hidden existence, and the sediments accumulate, recording time with a fidelity no surface lake can achieve. It is a world defined by quiet endurance, where the passage of time is measured not in days or years, but in millennia. And as we peer into these frozen reservoirs, we are reminded of our own fragility and our insatiable curiosity. We are drawn to these lakes not merely to catalog life or measure chemical signatures, but to connect with the deep, unbroken narrative of our planet. The ice above may appear inert and lifeless, but beneath it lies a heartbeat, a subtle pulse of water, life, and history that has persisted far longer than any human memory. In their silent depths, these frozen time capsules invite us to wonder, to respect, and to marvel at the endurance of life against the quiet, unyielding force of time. As we linger at the edge of these hidden waters, the enormity of what lies beneath the ice becomes almost impossible to grasp. The lakes are vast, dark, and silent, stretching across landscapes unseen by any human eye until recent decades. Their surfaces may shimmer faintly when illuminated by artificial light, but they are untouched, enigmatic, and eternal. Each lake is a universe unto itself, shaped by pressure, temperature, and isolation. They are records of resilience, testaments to the ability of life to endure in forms unimaginable, and mirrors of the Earth's own patient history. The extreme isolation of these lakes has created ecosystems that are fragile yet astonishingly self-sufficient. Microbial life has persisted for millions of years, evolving strategies to survive in complete darkness and under crushing pressure. They exist without sunlight, without seasonal cycles, without human interference. In their persistence, they redefine the boundaries of life. Some of these organisms metabolize minerals in the lake beds, while others extract energy from chemical reactions unknown in surface ecosystems. Their very existence challenges our understanding of biology, suggesting that life's tenacity may extend far beyond the conditions we consider habitable. The ice above, though seemingly immovable, is alive in its own way. It flows slowly, imperceptibly, carrying with it sediments, air bubbles, and records of the past. Each crack, each subtle shift in the glacier is part of a larger narrative, a dialogue between ice and rock, between pressure and water. It is this interplay that has created the lakes, carving out depressions, insulating the waters below, and preserving them for eons. Understanding this dynamic is crucial for scientists seeking to interpret the history contained within the waters. Every layer of ice is a chapter, every sediment a paragraph, and every microbe a sentence in the story of Earth's frozen frontiers. Human exploration of these lakes is both a scientific endeavor and a journey of humility. Polar expeditions face unimaginable challenges: sub-zero temperatures, violent winds, and the ever-present danger of crevasses and shifting ice. Yet, these risks are rewarded with glimpses into a world that has existed unchanged for millions of years. The first sterile drills that breached the icy ceilings revealed dark, still waters, and the initial analyses of these lakes brought discoveries that astonished the scientific community: new species, unique chemical balances, and biological processes that defied expectation. Each discovery raises new questions, fueling the insatiable curiosity that drives exploration. The frozen time capsules do more than preserve life. They preserve knowledge. Sediments and water chemistry capture traces of ancient climates, offering insights into the cycles of glaciation and warming that have shaped the planet. They allow us to reconstruct a past that predates human observation, to understand the Earth's rhythms on a scale that is almost incomprehensible. Every expedition, every sample, is a step toward reading these natural archives. They are windows into epochs long gone, silent witnesses to the evolution of continents, the ebb and flow of ice, and the emergence and survival of life in its most extreme forms. Yet, beyond the science, these lakes evoke wonder. There is a profound poetry in their existence, a reminder of patience, endurance, and the quiet majesty of nature. To stand on the surface of an ice sheet, knowing that beneath your feet lies water untouched for 1,000,000 years, is to confront both the fragility and resilience of life. It is to witness the persistence of Earth itself, and to realize that in this frozen expanse, life has survived where few would dare to imagine it possible. As the first chapter of this journey closes, we are left with a sense of awe and anticipation. The frozen time capsules are not just bodies of water. They are monuments to life, history, and the delicate balance of our planet. They challenge our understanding of survival, push the limits of exploration, and invite us to reflect on our place in the vast narrative of Earth. And as we prepare to delve deeper into these hidden worlds, mapping the invisible pathways beneath the ice, we carry with us a sense of reverence, a recognition that the most extraordinary stories are often those that remain hidden, waiting patiently for discovery. The frozen landscapes of the poles appear absolute, unyielding, and eternal. To the untrained eye, they are blank canvases of white, stretching endlessly to the horizon, their secrets hidden beneath layers of ice too thick and formidable to penetrate. Yet, beneath this apparent emptiness lies a hidden network of lakes, channels and pathways, subterranean worlds that defy imagination. Mapping these invisible domains requires more than courage. It demands ingenuity, precision, and a delicate marriage of technology and intuition. For centuries, humans believed the ice sheets were monolithic, impervious. Today, through a blend of science and imagination, we know otherwise. The ice conceals a dynamic, living landscape, teeming with geological and hydrological complexity. At the forefront of this revelation are ice-penetrating radar systems. Pulses of radio waves, emitted from aircraft or surface stations, penetrate the ice, bouncing back to reveal hidden topographies and the subtle undulations of the bed beneath. Through these signals, scientists can detect depressions, channels, and even pockets of liquid water. The images produced resemble ghostly maps, where shadows hint at forms concealed by centuries of ice. It is a meticulous process, each wave, each reflection analyzed, interpreted, and verified, translating abstract signals into tangible knowledge. These invisible pathways, once mere speculation, now emerge with increasing clarity, painting a picture of a hidden polar hydrology that rivals any surface landscape in complexity. Satellites orbiting hundreds of kilometers above the Earth provide another layer of insight. Sensitive to subtle changes in gravitational pull, ice thickness, and surface elevation, these instruments allow scientists to infer the presence of hidden lakes and channels, far beyond the reach of traditional exploration. Tiny variations in ice movement, the way glaciers subtly flex and flow, betray the existence of liquid reservoirs beneath. Each shift, each anomaly, tells a story of water trapped, of pressures balanced, and of life hidden in darkness. By combining radar and satellite data, researchers can produce maps that guide expeditions and focus drilling efforts, transforming abstract theory into actionable understanding. Yet, technology alone is not enough. Interpretation of these signals requires human insight, the ability to read patterns, to sense where anomalies might indicate water, sediment, or unique geological formations. The ice, though silent, communicates through its subtle rhythms, offering clues to those patient and attentive enough to notice. In this way, mapping the invisible is both a science and an art, the dance between data and intuition, between the precision of machines and the interpretive lens of human curiosity. The challenges of mapping these hidden lakes are formidable. Thick layers of ice, often several kilometers deep, distort signals and complicate analysis. Surface conditions are harsh, with temperatures plunging far below freezing and winds that sweep across the ice with relentless force. Crevasses and shifting glaciers threaten both equipment and personnel. And yet, the pursuit continues, driven by the promise of discovery, the possibility of uncovering lakes that have existed in isolation for millions of years, and the hope of glimpsing life that has survived in absolute darkness. Advances in autonomous technology have also transformed our understanding. Drones and robotic probes, capable of traversing glaciers and penetrating ice crevasses, bring us closer than ever to these hidden worlds. Equipped with sensors, cameras, and sampling tools, these machines can reach places humans cannot, capturing data that expands our knowledge while minimizing risk and environmental impact. Each mission yields glimpses of the subterranean landscape, revealing channels of liquid water weaving beneath the ice like veins in stone, lakes hidden in shadow, and pathways connecting previously isolated reservoirs. Mapping the invisible is not just about discovery. It is about understanding the dynamics of a planet in motion. The ice sheets are not static. They flow, they deform, and in their movement, they sculpt the hidden lakes beneath. Channels widen, depressions deepen, and new pathways emerge over centuries and millennia. By studying these processes, scientists gain insight not only into the lakes themselves, but also into the history of ice sheet dynamics, the behavior of glacial systems, and the forces that have shaped our planet over geological time. In these silent polar expanses, mapping becomes a bridge between imagination and reality. Each radar pulse, each satellite reading, each robotic probe brings the invisible into focus, revealing the intricate architecture of a world long hidden from view. It is a pursuit that combines technology, patience, and wonder, drawing humans ever closer to understanding the secrets beneath the ice, secrets that have endured in silence for millions of years, waiting for discovery. The process of revealing these hidden lakes is as meticulous as it is awe-inspiring. Ice-penetrating radar provides the first hints, but the signals are complex, distorted by layers of snow, ice, and air bubbles trapped over millennia. Each reflection must be carefully interpreted. What appears as a shadow or anomaly might be water, or it could be a layer of compressed ice, a pocket of sediment, or even a void formed by shifting glaciers. Scientists must cross-reference radar data with satellite imagery, surface measurements, and even seismic readings to confirm the presence of subglacial lakes. It is a painstaking puzzle, with each piece essential to building an accurate picture of the invisible. One of the most remarkable tools in this quest is airborne radar, flown over remote and dangerous terrain by skilled pilots and scientists. Suspended in fragile aircraft above ice plains, where temperatures can drop below -50 degrees Celsius, the radar emits pulses that penetrate kilometers of ice, mapping the contours of hidden lakes and channels below. From these flights, data emerge as ghostly topographies, revealing depressions that hold water, channels carved over eons, and lakes that stretch for dozens of kilometers in total darkness. Each discovery reshapes our understanding of the polar landscape, transforming what once seemed like lifeless plains into a labyrinth of hidden ecosystems and ancient reservoirs. But mapping is not merely a technical achievement, it is an act of imagination. Researchers must envision the spaces beneath their instruments, reconstructing three-dimensional landscapes from waves and signals, predicting how water flows under ice, and hypothesizing how these lakes have remained sealed for millions of years. It is a mental exercise in seeing the unseen, a combination of logic, intuition, and respect for the mysteries that resist full explanation. Even with advanced technology, the lakes retain an air of an enigma, reminding scientists that they are venturing into territories that no human has ever experienced directly. Robotic exploration has become increasingly vital. Autonomous probes, designed to drill through ice without contaminating the pristine waters, carry sensors that measure temperature, pressure, and chemistry. Cameras and sampling tools record the first glimpses of microbial life and sediment composition, bringing back evidence of ecosystems thriving in extreme isolation. These machines navigate crevices and channels, revealing hidden networks that link multiple lakes beneath the ice. Through their data, scientists begin to understand how water moves, how nutrients circulate, and how life adapts in a world that has never seen the sun. The invisible pathways are not uniform. Some channels are narrow, barely a few meters wide, carved by slow glacial movements and the pressure of ice above. Others are vast, shaped by millennia of flowing meltwater and subglacial streams. Some lakes are perched like mirrors beneath the ice, while others lie in valleys cut into ancient rock. Mapping these variations is crucial not only for understanding the lakes themselves, but also for interpreting the dynamics of the ice sheets above. Every crevice, every depression tells a story of pressure, heat, and time, of ice advancing and retreating, and of water persisting in the face of extreme conditions. As the mapping progresses, patterns emerge, revealing an interconnected system of lakes and channels. Some appear isolated, untouched for millions of years, while others show signs of intermittent connection, potential pathways where water and life could have migrated in the past. These insights challenge previous assumptions about the polar regions, painting a picture of a hidden world that is both dynamic and fragile, ancient yet surprisingly intricate. It is a world that exists parallel to the familiar surface, a silent network of reservoirs that has survived extreme cold, crushing pressure, and total darkness. Mapping the invisible is also an exercise in patience. Each expedition takes months of preparation, from calibrating instruments to navigating treacherous terrain. Data collection is slow, and interpretation is meticulous. Yet, the results are extraordinary. The ability to see the unseen, to chart waters sealed for 1 million years, and to glimpse ecosystems that have evolved in isolation. The maps that emerge are more than guides. They are portals to understanding, gateways into a realm of Earth that few have ever imagined, let alone observed directly. Through the combined efforts of radar, satellites, and autonomous technology, the invisible becomes visible, the inaccessible becomes accessible, and the hidden pathways of subglacial lakes unfold before human curiosity. Each new discovery sparks further questions, each map reveals new mysteries, and each expedition deepens our appreciation for the resilience of life and the ingenuity of the human mind in unraveling the secrets of our planet's frozen frontiers. As the invisible begins to reveal itself, the scale and complexity of the polar frontiers become increasingly apparent. What was once thought to be isolated, featureless expanses of ice now show intricate networks of lakes and channels, interconnected in ways that defy initial assumptions. The lakes are not solitary. They are part of a dynamic system shaped by pressure, heat, and the slow, inexorable flow of ice over millennia. Mapping these hidden corridors is like tracing veins in a living organism, understanding how water moves, pools, and interacts beneath layers of frozen time. Geophysical surveys provide more than mere outlines of hidden lakes. They capture motion. Ice is never still. Though it may appear solid and unyielding, glaciers are slow rivers of compressed snow and ice, moving imperceptibly yet inexorably. These movements create subtle variations in pressure and temperature beneath the surface, shaping subglacial landscapes in ways that radar alone can barely capture. Seismic studies, which send vibrations through the ice to measure how the ground responds, reveal the contours of lake basins and the composition of sediments below. With each new measurement, scientists refine their understanding, building ever more detailed maps of a hidden world. The human element in this exploration cannot be overstated. Teams of glaciologists, engineers, and geophysicists work together in some of the harshest environments on Earth, braving extreme cold, blizzards, and dangerous crevasses to collect data. Their efforts are guided by maps generated from previous radar flights, satellite imagery, and theoretical models, but nothing replaces the intuition and adaptability of those on the ground. When instruments fail or conditions shift unexpectedly, humans adjust, recalibrate, and improvise, translating abstract signals into meaningful knowledge. It is a collaboration between technology and human ingenuity, where curiosity drives every decision, and each discovery feels like a small triumph against the indifferent extremes of nature. The insights gained from mapping these hidden lakes extend beyond geography. They reveal the history of our planet. Variations in ice thickness, flow patterns, and lake distribution speak to climatic events from millions of years ago. They hint at periods of glacial advance and retreat, of ice melting and reforming, and of water carving pathways long before humans ever walked the Earth. In this way, mapping is not only a scientific endeavor, but a journey through time, uncovering evidence of processes that have shaped the planet on a scale beyond human perception. Each new lake discovered is a frozen diary entry, a preserved chapter in Earth's ancient narrative. The lakes themselves, revealed through mapping, display astonishing diversity. Some are perched high beneath thick ice, shielded from external forces and untouched for millennia. Others are broader, interconnected, and dynamic, with water flowing slowly between basins, perhaps carrying microorganisms and nutrients that have migrated over long time scales. The chemical composition of these lakes can vary dramatically, influenced by the minerals in bedrock, the pressure of the overlying ice, and the geothermal heat below. Mapping these differences is crucial to understanding how isolation affects life and how subglacial environments have evolved independently from surface ecosystems. Technological advances continue to push the boundaries of what is possible. Autonomous underwater vehicles, equipped with sonar, cameras, and sampling devices, navigate subglacial channels to collect data without contaminating pristine waters. They transmit images of sediments, microbial mats, and water movement, providing direct evidence that complements radar and satellite observations. Through this combination of remote sensing and in situ exploration, the invisible is slowly becoming tangible. We can now visualize the shapes of hidden basins, understand the flow of water beneath the ice, and witness the interaction of geological and biological forces in a realm previously thought unreachable. Yet, even as maps grow more detailed, mysteries remain. Entire networks of lakes may remain undiscovered, and the dynamics of water movement beneath ice sheets are still only partially understood. Each new expedition brings both answers and questions, reinforcing the sense that these polar landscapes, though mapped, are still alive with secrets. They remind us that our knowledge is limited, that the hidden pathways beneath the ice are as much a challenge to imagination as they are to science. In mapping the invisible, we gain not only knowledge, but perspective. We see how interconnected Earth's systems are, how life can persist in isolation, and how landscapes that appear static are constantly in motion. The maps themselves become a bridge, connecting human curiosity to the silent, resilient world beneath the ice, a world that has endured in darkness, waiting for the day it could finally be revealed. The final step in mapping the invisible is to bridge data into understanding, to take radar signals, satellite imagery, and robotic exploration, and weave them into a coherent vision of the hidden world beneath the ice. This synthesis is as much art as science. Patterns emerge from chaos, contours take shape from abstract signals, and previously hidden lakes are placed in context. revealing their relationships to one another and to the dynamic ice sheets above. With each new expedition, the maps grow more precise, more intricate, revealing a subterranean network of water, rock, and life that is as beautiful as it is alien. Mapping these hidden lakes has transformed our understanding of the polar regions. No longer are they seen as static, lifeless expanses. They are dynamic ecosystems, shaped by millennia of ice movement, pressure, and heat. Water flows through channels, sediments accumulate in basins, and microbial life persists against unimaginable odds. These insights are profound, not only for understanding Earth's extremes, but also for informing research into extraterrestrial environments. If life can survive in the darkness beneath a kilometer of ice, could it exist beneath the frozen crust of Europa, Enceladus, or other distant worlds? The maps that reveal Earth's hidden lakes may hold the blueprint for discovering life beyond our planet. Yet, the act of mapping is also an act of humility. The ice, so vast and imposing, reminds explorers of their smallness, of the limits of human perception, and of the patience required to uncover nature's secrets. Each measurement is painstaking. Each interpretation must be verified. Each expedition demands meticulous planning and execution, and even then, surprises await. New anomalies appear, unexpected channels are discovered, and the ice continues to shift, reminding us that the hidden lakes are part of a living, breathing system, not a static archive. The technology that enables these discoveries is remarkable. Satellites orbit silently, detecting subtle shifts in surface elevation and gravitational pull. Airborne radar penetrates ice sheets, revealing the contours of the frozen landscape beneath. Autonomous probes navigate channels, measuring chemical composition, temperature, and microbial life without disturbing fragile ecosystems. The integration of these tools allows us to peer into realms that were once considered unreachable, transforming speculation into knowledge and mystery into discovery. As these maps are refined, patterns of connectivity become clearer. Some lakes are entirely isolated, untouched for millions of years. Others appear linked by hidden channels, forming networks that may have allowed water and perhaps life to migrate beneath the ice over geological time. Understanding these connections is essential for interpreting the evolution of subglacial ecosystems, for predicting how these lakes respond to climate change, and for preparing safe, minimally invasive exploration. Each newly discovered pathway, each delineated basin, is a step toward comprehending a world that has existed in secrecy for far longer than humans have walked the earth. Mapping the invisible also carries a philosophical dimension. To see beneath the ice is to confront the limitations of perception, to recognize that what we assume to be empty or inert is often vibrant and complex. It challenges assumptions about isolation, survival, and the hidden forces shaping our planet. And it underscores a profound truth, that exploration is not merely about discovery, but about connection linking human curiosity to the ancient, resilient systems of Earth and understanding our place within a world far larger and older than ourselves. In the end, mapping is a prelude to exploration. It charts the pathways that scientists will traverse, the locations where drilling and sampling will take place, and the basins where life and history are preserved in isolation. It transforms invisible landscapes into navigable territories, offering both guidance and inspiration. Each map tells a story, not just of ice and water, but of perseverance, ingenuity, and the relentless pursuit of knowledge. As Chapter 2 concludes, the frozen expanse is no longer unknowable. We can see beneath the ice, trace the hidden waterways, and anticipate the lakes that have survived untouched for 1,000,000 years. The invisible has been partially revealed, yet mysteries remain, channels uncharted, basins unexplored, life forms yet unseen. Mapping has opened the door, but the journey continues. Beyond the data lies the promise of discovery, and the next step will take us closer to the heart of these hidden worlds, where life endures in darkness and the secrets of a million years await our understanding. Beneath the ice, in the shadowed depths of subglacial lakes, life persists in ways both miraculous and mysterious. Here, sunlight has never penetrated, and yet, microbial ecosystems thrive in absolute darkness. These organisms, invisible to the human eye, exist in isolation that spans millions of years, evolving independently of the surface world. Their survival is a testament to the tenacity of life, a reminder that even in the most extreme and unforgiving environments, existence finds a way. In these waters, untouched by wind, sun, or human influence, life has been forced to adapt, innovate, and endure, rewriting the rules of survival as we understand them. The extreme conditions of these lakes are staggering. Water trapped beneath kilometers of ice is cold, dark, and isolated from atmospheric oxygen. Nutrients are scarce, pressure is immense, and energy sources are limited to what can be extracted from minerals, chemical reactions, or geothermal heat. Yet, within this seeming desolation, life thrives. Microbes metabolize compounds in the sediments, convert chemicals into energy, and reproduce slowly but steadily. Some have developed entirely unique metabolic pathways, unseen in surface organisms, demonstrating that life is not confined to the conditions we consider favorable. These adaptations are not merely survival mechanisms. They are examples of evolution responding to the constraints of isolation and scarcity, producing ecosystems entirely self-sufficient and ancient. Scientists have long wondered how such life could exist for so long without external input. The answer lies in chemistry, geology, and patience. Minerals in lake beds provide a slow but steady source of nutrients, while chemical reactions between water and rock release energy that microbes can harness. The cold, while extreme, preserves DNA and cellular structures, slowing metabolism but prolonging life. These ecosystems are fragile yet enduring, delicate yet resilient, a paradox of existence that challenges assumptions about the boundaries of habitability. Studying these organisms requires extraordinary care. Human contact, even inadvertent contamination, could irreversibly alter these ecosystems. Drilling through kilometers of ice must be sterile, sampling protocols rigorous, and robotic probes meticulously controlled. Every measure is taken to ensure that the life forms we observe remain as pristine as they have been for millennia. In doing so, scientists are not merely studying biology, they're witnessing the endurance of life in its purest, most isolated form, a living testament to adaptation and resilience. The implications of life in these lakes extend far beyond Earth. If organisms can survive in complete darkness beneath ice for millions of years, it suggests that life may exist in similar environments elsewhere in the solar system. Europa, one of Jupiter's icy moons, is believed to harbor subsurface oceans beneath its frozen crust. Enceladus, orbiting Saturn, ejects plumes of water from its hidden ocean. The microbes thriving beneath our polar ice sheets offer a tantalizing glimpse into the possibilities of extraterrestrial life. They demonstrate that life is remarkably adaptable, capable of exploiting even the most marginal conditions, and they provide a model for what scientists might find when exploring other worlds. Despite their microscopic size, these organisms have outsized significance. They preserve records of chemical processes, energy flows, and evolutionary strategies that have persisted over geological time. Studying them allows us to understand how life endures under constraints far beyond human experience, and how ecosystems can function independently of sunlight and atmospheric input. Every sample, every analysis, reveals the strategies life has devised to persist, adapt, and survive. A lesson in resilience written in the language of biology. These ecosystems are also mirrors reflecting Earth's past. The isolation of subglacial lakes has preserved ancient lineages, chemical signatures, and even remnants of climates long vanished. They act as living fossils, maintaining continuity with a world that existed before modern humans. Before continents had fully shifted into their current configurations, and before the ice sheets themselves reached their present extent. In studying them, we peer into the deep history of life, witnessing adaptations that have been honed over millennia, surviving in a world of darkness, cold, and isolation. In these silent, hidden waters, the pulse of life continues, steady and enduring. Each organism, each metabolic reaction, each microbial colony is a testament to persistence, a reminder that even in the most extreme isolation, life does not surrender. As we begin to explore these hidden ecosystems, we confront not only the biology of survival, but also the philosophical magnitude of existence in the shadows, a world where life endures in eternal darkness, quietly defying the odds. Beneath the ice, the microbial worlds are extraordinarily diverse. In each lake, life has carved out niches in response to the harsh and unyielding environment. Some microbes cling to the sediments at the lake floor, feeding on minerals and decaying organic matter preserved for millennia. Others drift in the water column, absorbing chemical energy dissolved in the icy waters. Each species occupies its own ecological niche, forming a fragile balance where survival depends on precision, cooperation, and adaptation. Unlike surface ecosystems, where sunlight drives productivity, these communities rely entirely on chemical energy chemosynthesis, a process that converts inorganic compounds into life-sustaining energy. The scale of time involved is staggering. In some lakes, organisms may divide only once every 100 years, a pace of life dictated by the scarcity of nutrients and the extreme cold. In this suspended rhythm, evolution continues at a slow, deliberate pace, creating lineages and adaptations that are alien to scientists accustomed to faster surface-dwelling life. Each microbial colony becomes a living archive, a reflection of millions of years of uninterrupted evolution, untouched by competition, contamination, or climate shifts above the ice. Despite the extreme conditions, these organisms demonstrate remarkable ingenuity. Some extract energy from sulfur compounds or methane trapped in sediments, converting what might seem like inhospitable chemicals into sustenance. Others have adapted to survive high pressures and near-freezing temperatures, developing proteins and cellular structures that function in ways impossible on the surface. The creativity of life in these lakes challenges our understanding of biology, revealing that adaptability is far more flexible than previously imagined. Life in isolation also preserves ancient genetic material. DNA extracted from subglacial microbes often contains sequences that are unique, with no known counterparts in surface organisms. These sequences provide a glimpse into evolutionary experiments conducted in solitude over millions of years. They are not merely biological curiosities. They are evidence that life has persisted in hidden corners of the planet, independently exploring pathways of adaptation that may never have occurred elsewhere. Studying these ecosystems requires careful precision. Scientists employ sterile drilling techniques to prevent contamination, ensuring that every sample represents the natural state of the lake. Robots and automated probes collect water, sediments, and even microorganisms without disrupting the delicate balance of these hidden worlds. Each observation, each measurement, is a glimpse into life as it has evolved under absolute isolation, providing insights that could inform not only biology, but also the search for life on other planets. The existence of these microbial ecosystems raises profound questions about resilience and survival. If life can endure for millions of years in total darkness, what does this tell us about the fundamental nature of life itself? Is adaptability intrinsic to all living things, or are these microbes extraordinary exceptions? In observing them, scientists are confronted with the limits of their imagination, challenged to consider possibilities for life in environments that were once thought uninhabitable. These ecosystems are also silent witnesses to Earth's history. The chemistry of their waters, the composition of sediments, and the metabolic pathways of microbes preserve information about past climates, ice sheet movements, and geochemical processes. Each organism, each colony, is part of a living record, maintaining continuity with a time long before humans existed. In a sense, the microbes are archivists, carrying within them the story of Earth's hidden past, surviving where most life would fail, and offering a window into epochs untouched by the surface world. And yet, life in eternal darkness is not static. Though slow and subtle, changes occur. Microbial populations fluctuate, chemical balances shift, and sediments settle and accumulate. Even in isolation, the lakes are dynamic ecosystems, responsive to forces within and beneath the ice. Their endurance is not mere stasis. It is adaptation, a delicate choreography of survival unfolding silently over millions of years. In these hidden waters, the boundaries of life are tested, expanded, and redefined. Microbial ecosystems beneath the ice challenge our perception of habitability, resilience, and the persistence of life. They teach us that life is not merely a product of sunlight and surface conditions, but a force capable of thriving in isolation, darkness, and extreme pressure. As we continue to explore these hidden frontiers, we are not merely cataloging life. We are witnessing the poetry of survival in its most extraordinary form. Life in eternal darkness is a lesson in perseverance. The organisms inhabiting subglacial lakes have evolved strategies that challenge conventional understanding. Without sunlight, photosynthesis is impossible, yet chemical energy suffices. Microbes oxidize iron, sulfur, and other minerals, converting chemical reactions into life-sustaining processes. Some even rely on gases trapped in sediments, methane, carbon dioxide, or hydrogen to fuel metabolic pathways unseen on the surface. In this hidden world, survival depends not on abundance, but on ingenuity, patience, and the ability to exploit resources invisible to the outside observer. Isolation has driven evolutionary divergence. Microbes in separate lakes, even those a few kilometers apart, often exhibit remarkable genetic differences. Deprived of migration and mixing, each population has charted its own evolutionary course for millions of years. These differences are not superficial. They represent entirely new metabolic capabilities, novel enzymes, and unique biochemical strategies. The lakes become natural laboratories of evolution, demonstrating how life can diversify under extreme isolation, forming ecosystems completely distinct from those on the surface. The study of these organisms also provides insight into resilience under extreme conditions. Many microbes are psychrophiles, cold-loving organisms that thrive at near-freezing temperatures. Others are piezophiles, adapted to survive extreme pressure from the kilometers of ice above. Still others have developed remarkable tolerance to nutrient scarcity, with metabolic rates so low that survival depends on slow, deliberate cycles stretching over centuries. Each adaptation is a story of persistence, a demonstration that life can endure when most would fail, exploiting niches invisible and inaccessible to humans. Yet life here is fragile. The ecosystems are balanced with exquisite precision. Small changes in chemical composition, temperature, or sediment influx could disrupt these ancient communities. Even the act of human exploration carries risk. Contamination from drilling, introduction of foreign microbes, or chemical interference could irreversibly alter ecosystems that have existed unchanged for millions of years. Consequently, every expedition must combine curiosity with caution. Every probe must be sterilized, and every procedure meticulously planned. Preservation is as critical as discovery. Microbial life also serves as a historical record. The composition of water, the arrangement of sediments, and the metabolic strategies of organisms provide insight into Earth's past. Traces of ancient climates, ice sheet movements, And geochemical changes are preserved not only in sediments, but within the microbes themselves. They are living witnesses to epochs long before human observation, carrying the history of ice and water in their very cells. In this sense, life beneath the ice is both present and historical, a bridge between biological endurance and the planet's deep past. The diversity and ingenuity of life in these lakes expand the definition of habitability. If life can survive here, in darkness, isolation, and extreme pressure, it suggests that other environments once thought inhospitable may, in fact, support life. Subglacial lakes provide analogs for extraterrestrial ecosystems, helping scientists develop strategies to search for life on icy moons and planets. The metabolic strategies, genetic adaptations, and chemical interactions observed here are not merely academic curiosities. They are templates for imagining life beyond Earth. In this darkness, life persists quietly, without spectacle, but with remarkable persistence. Microbial communities thrive, evolve, and interact in ways that are invisible to the eye yet profound in their implications. They remind us that survival is not always loud or visible. Sometimes it is slow, deliberate, and hidden, yet no less extraordinary. These ecosystems challenge assumptions, provoke questions, and expand our understanding of what it means to live. As we continue to explore the lakes beneath the ice, the hidden pulse of life becomes more apparent. Microbes thriving in eternal darkness are not anomalies. They are exemplars of resilience, teaching that life's boundaries are broader than imagination alone could conceive. They invite us to reflect on the tenacity of existence, the ingenuity of adaptation, and the enduring power of evolution in the planet's most extreme frontiers. The final understanding of life in eternal darkness comes not from a single discovery, but from the patterns that emerge across lakes, sediments, and microbial communities. Each lake, though isolated, tells a similar story. Life persists, evolves, and adapts in silence, unaffected by sunlight or atmospheric change. In this hidden realm, ecosystems have been shaped over millions of years by forces both subtle and immense: pressure, chemistry, and the slow movement of ice above. The organisms here are not relics. They are active participants in a delicate balance, forming self-sustaining networks that challenge our understanding of life itself. One of the most remarkable features of these ecosystems is their efficiency. In the absence of abundant resources, life has optimized its strategies to survive and thrive. Metabolic pathways are streamlined, energy consumption is minimal, and reproductive cycles are slow but steady. Microbes exploit every chemical opportunity, drawing sustenance from compounds locked in sediments or dissolved in the water. In a world where survival depends on patience and precision, life has become exquisitely attuned to its environment, demonstrating resilience that spans geological time. Isolation has led to evolutionary creativity. Many microbes possess genes that have no known equivalents on the surface, encoding enzymes and metabolic mechanisms entirely unique. These adaptations are responses to extreme cold, crushing pressure, and scarce nutrients. They reveal that life is not constrained by conditions familiar to humans, but can exploit virtually any ecological niche, no matter how remote or challenging. Each gene, each metabolic process, represents an experiment in survival conducted over millions of years, a testament to nature's ingenuity in environments where traditional energy sources are absent. The chemical composition of subglacial lakes plays a critical role in sustaining life. Some lakes are rich in methane or sulfur compounds, others in dissolved minerals, and all contain subtle gradients of nutrients that microbes exploit with precision. Even the sediments themselves serve as repositories of energy, slowly releasing compounds that sustain microbial colonies. Life in these lakes is not static. It interacts with its environment in a feedback loop, altering chemical concentrations, sediment layers, and even the structure of microbial communities over time. In this dynamic equilibrium, survival is not merely endurance, It is adaptation, evolution, and quiet innovation. Studying these ecosystems requires extreme care. Drilling through kilometers of ice must avoid contamination, and robotic probes must navigate fragile environments without disrupting them. Every sample is precious, every measurement carefully controlled. Scientists are not merely observers. They are custodians of worlds that have endured for 1,000,000 years, charged with preserving their purity while uncovering their secrets. The stakes are high, but the rewards are profound. A glimpse into life's ingenuity, a window into evolution unspoiled by human interference, and insights that may inform our search for life beyond Earth. The existence of life in eternal darkness reshapes our perspective on habitability. It demonstrates that ecosystems can thrive without sunlight, that life can endure under crushing pressures and extreme cold, and that isolation does not preclude diversity or complexity. The lakes beneath the ice are not barren voids. They are laboratories of adaptation, where evolution has operated uninterrupted, creating organisms with capabilities that challenge our understanding of biology. In these hidden waters, life is at once fragile and unyielding, delicate in balance yet resilient in persistence. Life in these lakes also preserves history. Microbes carry within them genetic information reflecting ancient conditions, chemical interactions, and evolutionary pressures that have persisted for millennia. The sediments and water chemistry serve as archives of geological and climatic changes, creating a living record of the planet's hidden past. To study these ecosystems is to study both biology and history, to witness survival and memory intertwined in a frozen, isolated world. As Chapter 3 concludes, the lesson of these lakes is clear. Life endures where it must, adapts to the unimaginable, and thrives in the silence of isolation. The hidden microbial communities beneath the ice are a testament to resilience, a demonstration of evolution's creativity, and a mirror reflecting possibilities for life far beyond our planet. In eternal darkness, life persists, quietly defying the odds, patiently awaiting discovery by those willing to peer beneath the frozen frontiers of Earth. The ice that blankets polar landscapes is more than a frozen expanse. It is a vault of history, a living archive, and a window into the planet's deepest secrets. Each layer of snow compressed into ice carries with it chemical signatures, trapped gases, and microscopic particles that tell the story of Earth's past. For millennia, these frozen layers have recorded volcanic eruptions, atmospheric shifts, climate changes, and even traces of life. Beneath this serene whiteness lies a world where time is preserved, where the narrative of the planet is locked in crystalline form, waiting for scientists to decipher its hidden messages. Ice cores extracted from these sheets are extraordinary time capsules. By carefully analyzing their composition, researchers can reconstruct climates stretching back hundreds of thousands of years. Tiny air bubbles trapped within the ice preserve ancient atmospheres, capturing carbon dioxide, methane, and other gases that reveal fluctuations in climate long before humans walked the Earth. Layers of dust, pollen, and microscopic organisms offer clues about vegetation, wind patterns, and even volcanic eruptions. Each layer is a page in a chronicle written over millennia, and by studying them, scientists can read the history of the planet with unprecedented precision. The ice also conceals physical landscapes that would otherwise be invisible. Beneath kilometers of frozen water lie valleys, ridges, and subglacial lakes, sculpted over eons by the slow, relentless movement of glaciers. The ice acts as both preserver and protector, shielding these hidden features from erosion, decay, and external forces. Radar and satellite imaging allow researchers to detect these formations, revealing vast, intricate networks that rival any surface topography in scale and complexity. These hidden landscapes provide clues about past glacial activity, water flow, and geological processes that have shaped the continent over millions of years. Embedded within the ice are also traces of life that have long since disappeared from the surface. Microbes, spores, and pollen captured in snow and ice layers act as biological time capsules, preserving genetic material from eras when conditions were drastically different. These samples allow scientists to study evolution, adaptation, and extinction on a scale impossible on the surface. The frozen environment safeguards these materials, slowing decay and maintaining structures that can survive for hundreds of thousands of years. In this way, ice becomes a guardian of biological history, a medium through which we can access the planet's living past. Ice is dynamic, not static. Though it may appear immovable, glaciers flow slowly yet persistently, carving landscapes, creating pressure ridges, and influencing the distribution of subglacial lakes. The movement of ice shapes not only the surface, but also the hidden world beneath. By studying patterns of flow, scientists can understand how water is stored and released, how lakes interact, and how life beneath the ice persists despite extreme isolation. The interplay between pressure, heat, and movement creates a delicate balance, maintaining the lakes and preserving ecosystems that have endured for millions of years. The secrets within ice are also chemical. Snow and ice capture trace elements from the atmosphere, from dust carried thousands of kilometers, and from volcanic eruptions that released ash into the skies. These chemical signatures act as markers of past events, providing a timeline of natural phenomena and environmental changes. Scientists can measure isotopes, concentrations of gases, and particulate matter to reconstruct temperature trends, precipitation patterns, and even the frequency of natural disasters. Each core extracted is like a detective's case file, revealing events that shaped the planet long before humans attempted to document them. Human exploration of these icy archives is a delicate endeavor. Drilling must be precise, with sterile equipment to prevent contamination, and extraction carefully planned to maintain the integrity of the ice. Each core is treated as both a scientific specimen and a historical document, analyzed layer by layer to extract maximum information. The work is painstaking, often conducted in extreme cold, high winds, and remote conditions, yet the insights gained are profound. In the ice, we encounter the intersection of geology, chemistry, and biology, uncovering connections between climate, life, and Earth's evolutionary history. As we begin to unravel the secrets hidden within the ice, we realize that these frozen layers are far more than inert matter. They are storytellers, archivists, and sentinels of time. Every bubble, sediment, and particle is a message from the past, waiting to be read. The ice preserves not just history, but also lessons for the future, lessons about resilience, adaptation, and the delicate balance of Earth's systems. It is a reminder that beneath the apparent stillness lies complexity, life, and knowledge that continues to inspire and challenge our understanding. The deeper we delve into the ice, the more intricate its story becomes. Ice cores reveal sudden shifts in chemical composition, abrupt changes in isotopes, and layers that mark dramatic climatic events. Some layers contain traces of volcanic eruptions, the ash carried thousands of kilometers by high-altitude winds, settling gently upon the snow before being sealed by subsequent snowfall. Others reflect periods of intense wind, drought, or even meteorite impacts, each event immortalized in the crystalline layers. The ice is both a mirror and a memory, capturing the Earth's triumphs and catastrophes in silent testimony. Embedded in this frozen record are microscopic clues to life itself. Pollen grains, fungal spores, and ancient microbes testify to ecosystems long vanished from the surface. Their preservation is astonishing. Some spores remain viable after hundreds of thousands of years, offering glimpses into ancient plant life and the resilience of organisms against time and extreme conditions. Through careful analysis, scientists can reconstruct past biomes, trace shifts in vegetation, and even infer how ecosystems responded to climate changes over millennia. Ice, in this sense, becomes a bridge between biology and geology, a medium where the histories of life and Earth converge. The pressure and weight of ice, though seemingly oppressive, play a crucial role in maintaining these hidden records. Glaciers flow slowly, grinding over bedrock and reshaping the landscape beneath. Yet they also act as protective shields, preventing the decay of sediments and organisms below. Subglacial lakes remain sealed from the surface, insulated by kilometers of ice, preserving waters and ecosystems in pristine condition. It is within this interplay of pressure, movement, and isolation that the secrets of the ice are safeguarded, a delicate balance between preservation and transformation. Technological advances have revolutionized our ability to access and interpret these frozen archives. High-resolution radar imaging allows scientists to visualize subglacial lakes and the contours of bedrock beneath kilometers of ice. Satellite monitoring detects subtle shifts in ice flow, thickness, and surface elevation, providing clues to the dynamics of glaciers and hidden water networks. Drilling techniques, refined over decades, allow researchers to extract ice cores without contaminating their precious contents. Robotic probes navigate crevassed terrain and subglacial channels, capturing chemical and biological data that complement traditional observations. Through these methods, the secrets preserved for millennia are revealed with unprecedented clarity. Each discovery within the ice adds nuance to our understanding of Earth's history. Variations in isotopes indicate periods of warming and cooling, revealing cycles of glaciation and retreat. Sediment layers show erosion patterns and ancient river flows, while chemical signatures reflect changes in atmospheric composition over geological timescales. Together, these data form a multidimensional map of Earth's environmental evolution, a record far richer and more detailed than surface observations alone could provide. In essence, ice acts as both historian and archivist, preserving narratives that span millions of years. The ice also holds keys to understanding future climate. By studying past fluctuations, scientists gain insight into the mechanisms driving global warming, ice sheet stability, and sea level changes. Patterns revealed in ice cores can forecast how polar regions may respond to continued temperature increases, offering a rare glimpse into the long-term consequences of environmental shifts. In this way, the secrets of the ice are not just historical. They are profoundly relevant to the present and future, guiding humanity in a world of accelerating change. Yet, for all its scientific value, ice retains an aura of mystery. Hidden pockets, unexplored lakes, and isolated ecosystems remain beyond human reach. The frozen layers are simultaneously revealing and concealing, offering knowledge while reminding us of the limits of our understanding. In these hidden depths, the ice challenges both technology and imagination, inviting exploration while guarding its most intimate secrets. As we continue to study the frozen archives, one truth becomes clear: ice is more than frozen water. It is a record of life, climate, and geological transformation, a preserver of ancient ecosystems, and a window into the Earth's hidden processes. It bridges the past and the present, the living and the inert, offering lessons in resilience, adaptation, and the passage of time. Beneath its surface lies a world waiting to be deciphered, a silent, enduring testament to the planet's extraordinary history. The secrets held within the ice are not merely chemical or geological. They are profoundly biological. Subglacial lakes, preserved beneath kilometers of ice, harbor ecosystems that have evolved in total isolation. Life in these hidden waters exists in delicate balance, shielded from sunlight and atmospheric change, yet thriving through chemical energy and adaptation. Ice acts as both guardian and barrier, keeping these ecosystems pristine and intact, while the surface world remains oblivious to their existence. By studying the ice above and the lakes below, scientists glimpse the extraordinary interplay of geology, chemistry, and biology over millennia. The pressure of the overlying ice shapes not only the physical landscape, but also the habitats it conceals. Water beneath glaciers flows slowly, carving channels, feeding lakes, and influencing the distribution of nutrients. This dynamic movement ensures that the lakes are not static reservoirs, but living systems, capable of supporting life and preserving it through the ages. Sediments carried by meltwater contain minerals and compounds that provide energy sources for microbial communities, sustaining life where sunlight never penetrates. Each subglacial lake is a self-contained laboratory, isolated yet dynamic, a natural experiment in resilience and survival. Ice cores reveal astonishing temporal depth. By examining layers formed over hundreds of thousands of years, scientists reconstruct not only past climates but also changes in chemical composition, sedimentation, and potential biological activity. Some microbes trapped in these layers remain viable, capable of revival under laboratory conditions, providing a direct connection to ancient life. This frozen archive offers unparalleled insight into evolutionary processes, survival strategies, and the mechanisms by which life persists under extreme constraints. The ice becomes a time machine, allowing humanity to study life and environments far removed from the present. Technological innovation is key to unlocking these secrets. Airborne radar maps subglacial landscapes, revealing lakes, valleys, and channels hidden beneath the ice. Satellite data provides surface indicators, such as shifts in ice flow or elevation changes, which hint at dynamic processes below. Robotic probes penetrate lakes, collecting chemical and biological samples without disturbing fragile ecosystems. Each technological advance extends our reach into this hidden world, transforming speculation into tangible discovery. The ice, once a barrier, becomes a medium through which the hidden workings of Earth can be observed and understood. The information encoded in ice is multi-layered. Air bubbles preserve past atmospheres, isotopes indicate temperature fluctuations, and sediments reveal erosion, volcanic events, and past water flows. Even subtle differences in chemical composition can point to the presence of microbial life or previously unknown geological processes. Each piece of data contributes to a broader understanding of the Earth system, linking atmospheric conditions, climate change, and life in a single, continuous narrative. In this way, ice becomes both a mirror of the past and a guide for the future. Life preserved beneath the ice is not passive. Microbes metabolize minerals, recycle nutrients, and interact with sediments, influencing the chemical and physical environment. Even in isolation, ecosystems are dynamic, shaped by pressure, chemistry, and the slow movement of water. The balance is delicate, but the persistence is extraordinary. For millions of years, life has adapted to survive, evolve, and maintain itself in a world of darkness and cold. These systems challenge assumptions about the conditions necessary for life, offering models for resilience and adaptation that extend beyond Earth. Studying the ice also reveals the fragility of these preserved worlds. Human intrusion, contamination, or climate-induced changes could irreversibly alter ecosystems that have existed for eons. As exploration expands, researchers must balance curiosity with caution, ensuring that the frozen archives and hidden lakes remain protected. The ice, though robust in its preservation, is sensitive to disruption. Maintaining the integrity of these ecosystems is as critical as uncovering their secrets. In understanding the ice, we begin to see Earth's history as a layered story of climates, of life, of geological transformation, and of survival in extreme isolation. The frozen landscape is not merely a backdrop. It is an active participant in the planet's evolution, preserving, shaping, and sustaining hidden worlds. Beneath the serene surface lies a complex interplay of forces, a dynamic network of life, water, and rock, all recorded in crystalline layers that have endured for millennia. The secrets within the ice remind us that even in apparent stillness, The planet is alive with history and possibility. The final revelations of the ice lie in its capacity to preserve both mystery and meaning. Beyond serving as a record of climate and life, it safeguards knowledge of processes that shape the planet's hidden frontiers. Ice is both witness and participant, a medium through which time, geology, and biology converge. Every layer, from the thinnest snowflake compressed into crystal to the deepest, densest ice thousands of years old, carries a story. These stories reveal the Earth not as a static entity, but as a dynamic system continually evolving, quietly reshaping itself beneath the surface. Subglacial lakes, concealed beneath these layers, owe their existence to the very ice that shields them. They are cradled by pressure, insulated from external changes, and maintained by subtle geothermal heat and glacial flow. These lakes are natural laboratories where water, rock, and life interact in isolation, forming ecosystems that have persisted for millions of years. The ice ensures their preservation, simultaneously creating a barrier to human intrusion and a window into resilience, adaptation, and survival under extreme conditions. Each lake is a world unto itself, sealed in darkness, yet full of activity invisible to the outside observer. The physical properties of ice play a critical role in this preservation. The density and stratification of ice regulate pressure and temperature, maintaining conditions that are remarkably stable over time. Trapped gases provide snapshots of ancient atmospheres, while embedded dust, volcanic ash, and organic material record surface conditions, climatic events, and biological activity. These features, layered meticulously over millennia, create a chronological tapestry of Earth's history, one that scientists can interpret to understand both past and potential futures. Ice, in this sense, becomes both canvas and archive, chronicling the planet's ongoing narrative. Technological advances have been crucial in decoding these frozen messages. Airborne radar surveys reveal hidden lakes, valleys, and channels beneath kilometers of ice. Satellite observations detect minute shifts in elevation, ice flow, and surface structure, indicating dynamic processes at work below. Sterile drilling and robotic probes allow scientists to sample ice and water without disturbing the delicate balance of preserved ecosystems. Through this integration of technology and observation, the secrets of the ice, its chemistry, history, and life become accessible, allowing humanity to read a record of Earth's evolution with unprecedented clarity. The biological dimension is particularly profound. Microbes trapped in ice layers or thriving in subglacial lakes demonstrate the adaptability and persistence of life. They survive in darkness, under crushing pressure, and with minimal energy sources, offering living examples of resilience that extend beyond Earth. Studying these organisms allows scientists to understand metabolic adaptations, evolutionary strategies, and the boundaries of life itself. In doing so, ice becomes more than a historical record. It is a cradle of biological insight, preserving lessons from ecosystems that have endured in isolation for millions of years. Beyond biology and chemistry, the ice also teaches lessons in patience and observation. Extracting its secrets requires meticulous care, long-term commitment, and respect for the fragile systems it preserves. Each core extracted, each layer analyzed, each microbial sample examined is a step in understanding Earth's complex history. The frozen archives demand humility, reminding researchers that discovery is gradual, layered, and often constrained by the limits of technology and human endurance. Yet, for all its scientific value, ice retains an element of mystery. Unexplored subglacial lakes, hidden valleys, and isolated ecosystems remain beyond reach, reminding us that the planet still holds secrets that resist human knowledge. These unknowns inspire curiosity, inviting further exploration while highlighting the delicate balance between study and preservation. In the ice, every discovery brings new questions. emphasizing that the pursuit of understanding is as infinite as the frozen landscapes themselves. As Chapter 4 concludes, the lesson of the ice is clear. It is both archive and protector, history and laboratory, barrier and window. Beneath its serene surface lies a world of dynamic interaction, of water, life, and geology waiting to be deciphered. The secrets within the ice illuminate Earth's past, inform its present, and guide our understanding of the future. In their frozen depths, we find not only knowledge but inspiration, a reminder that the planet is alive with stories, resilience, and mysteries, all preserved in the crystalline memory of ice. The polar regions have always held a magnetic pull on human imagination, a place of extremes, of ice and silence, where survival itself is a triumph. Yet beneath the seemingly unbroken white expanses lies a world of astonishing complexity, where hidden lakes, subglacial rivers, and ancient ice converge to form a landscape that is as dynamic as it is secretive. Unlocking these polar mysteries requires courage, technology, and vision, bridging the gap between the visible surface and the hidden forces operating below. At the forefront of this exploration are subglacial lakes, sealed away for millions of years, each one a repository of Earth's history and life. They are inaccessible in ways that challenge both engineering and imagination. Drilling through kilometers of ice without contaminating these pristine ecosystems is an extraordinary technical feat, demanding precision, sterility, and innovation. Each probe, each extraction, is a high-stakes venture, an opportunity to observe life that has existed in complete isolation, untouched by sunlight or human influence, and a chance to understand the processes that have shaped these frozen landscapes over geological time. The discoveries made in these hidden waters are reshaping our understanding of the planet. Microbial life has persisted in conditions previously thought inhospitable, surviving in darkness, extreme cold, and under immense pressure. The biochemical pathways these organisms employ are unprecedented, revealing strategies of energy use, survival, and adaptation that challenge conventional biology. In isolation, evolution has taken unexpected turns, creating life forms and ecosystems entirely independent from the surface world. The lakes, therefore, are not just scientific curiosities. They are living laboratories of evolution, revealing the limits and possibilities of life itself. Mapping these regions is no small task. Radar surveys, satellite imagery, and seismic studies combine to reveal the contours of hidden valleys and the outlines of lakes that have never seen sunlight. Each new map illuminates the intricacies of water flow, the distribution of sediments, and the potential habitats for life. The process is painstaking, often requiring multiple expeditions, repeated measurements, and careful analysis of ambiguous signals. Yet each successful survey adds depth to our understanding, revealing networks of lakes and channels that form a hidden hydrological system, interconnected beneath the ice in ways only now becoming visible to science. Technological innovation drives progress in these extreme conditions. Autonomous underwater vehicles navigate subglacial lakes, capturing images, collecting samples, and measuring chemical properties without disturbing fragile ecosystems. Advanced drilling techniques penetrate ice sheets while maintaining sterility, preserving the delicate balance of the lakes below. Satellites track ice movement, surface elevation changes, and subtle thermal anomalies, providing insight into dynamic processes that occur over millennia. Through the integration of these technologies, humans are finally able to access a world that, until recently, existed only in theory and imagination. The insights gained extend far beyond the poles. Understanding life beneath the ice informs our search for extraterrestrial habitats. Europa, Enceladus, and other icy moons in our solar system may harbor subsurface oceans shielded from sunlight. The microbes thriving in Earth's hidden lakes offer models for potential life in these alien environments, showing that survival is possible under conditions previously considered uninhabitable. The polar frontiers, therefore, are not only Earth's secrets, they are guides to understanding life elsewhere in the cosmos. Each discovery carries philosophical weight. The isolation and resilience of subglacial ecosystems challenge assumptions about the necessity of sunlight, abundance, and connectivity for life. They reveal the persistence of life against extreme odds and the ingenuity inherent in evolution. They also underscore the fragility of ecosystems that have endured for millions of years, emphasizing the responsibility of humanity to explore without causing irreversible harm. The polar mysteries are as much about stewardship as discovery, highlighting the delicate balance between curiosity and preservation. As we stand on the brink of further exploration, the polar regions remind us that the planet's greatest secrets often lie hidden beneath the surface. The lakes, ice cores, and subglacial networks offer not only scientific knowledge, but also insight into resilience, adaptation, and the power of time. Unlocking these mysteries is a journey into Earth's deepest archives, where history, life, and geology converge in silent testimony to the enduring forces of nature. Beneath the frozen surface, subglacial lakes form interconnected networks that challenge our understanding of Earth's hydrology. Channels carved by slow-moving ice carry water from one basin to another, forming systems that have persisted in isolation for millions of years. These hidden flows are not only physical phenomena, they are ecological highways, shaping the distribution of microbial life, transporting nutrients and sustaining ecosystems sealed away from the surface. Mapping these networks reveals a complex and dynamic underworld, one where the principles of geology, chemistry, and biology intertwine in ways both subtle and profound. The physical properties of ice play a crucial role in preserving these hidden worlds. The immense weight of glaciers creates pressure that maintains subglacial lakes in liquid form despite sub-zero temperatures. Heat from the Earth's interior seeps upward, preventing complete freezing and enabling the slow circulation of water. These conditions, stable over millennia, provide a refuge for life, insulating ecosystems from the dramatic climate fluctuations experienced at the surface. The ice is both a shield and a conduit, simultaneously protecting these environments and shaping their internal dynamics. The exploration of these lakes requires ingenuity. Scientists deploy autonomous probes that navigate subglacial waters, measuring temperature, salinity, and chemical composition while capturing imagery of otherwise invisible landscapes. Drilling through kilometers of ice demands extreme precision and sterility, ensuring that the delicate ecosystems remain untouched by external contamination. The technology is as sophisticated as it is delicate, a marriage of engineering and environmental ethics. Every expedition is a careful negotiation between curiosity and responsibility, a testament to human ingenuity applied to the most extreme frontiers of the planet. The life forms found within these hidden waters are as extraordinary as the environments they inhabit. Microbes metabolize chemical compounds, recycle nutrients, and interact with sediments in ways that demonstrate evolutionary creativity under isolation. Genetic analysis reveals pathways entirely unknown in surface organisms, offering new insights into the adaptability and limits of life. In these waters, life operates at the edge of possibility, thriving in darkness, under immense pressure, and with scarce energy sources. The ecosystems are small in scale, yet vast in significance, illuminating the resilience and inventiveness of biology when faced with extreme constraints. Understanding these systems has implications far beyond the poles. The metabolic strategies and adaptations of microbes in subglacial lakes offer clues about potential life on icy moons like Europa and Enceladus. These analogs suggest that life may exist in environments previously considered uninhabitable, guided by chemical energy rather than sunlight. Studying Earth's hidden lakes thus becomes a window into the broader possibilities of life in the cosmos, revealing that the principles of survival are universal, not confined to familiar terrestrial conditions. Yet, for all the technological and scientific achievements, the polar regions retain an aura of mystery. Many subglacial lakes remain undiscovered, hidden beneath kilometers of ice, and accessible only through inference and indirect measurement. Each new survey uncovers anomalies, unexpected channels, or basins whose existence challenges prior assumptions. The unknown stretches endlessly, a reminder that exploration is not simply a matter of observation, but of imagination, interpretation, and patience. The poles are a living puzzle, where every discovery deepens understanding while revealing new layers of complexity. The pursuit of knowledge in these regions is a delicate balance. Human presence, however well-intentioned, carries the risk of disrupting ecosystems that have endured for millions of years. Contamination, chemical interference, or physical disruption could permanently alter these pristine worlds. As a result, exploration is guided by principles of stewardship, emphasizing minimal impact, meticulous planning, and ethical responsibility. The mysteries of the ice demand not only curiosity but respect, acknowledging that we are visitors in environments older and more enduring than humanity itself. As Part 2 concludes, the hidden lakes beneath the ice are no longer theoretical curiosities. They are real, dynamic, and complex systems. They embody the convergence of geology, hydrology, biology, and time, offering insights into resilience, adaptation, and the hidden processes that shape our planet. Unlocking the polar mysteries is a journey into these frozen frontiers, a quest to understand life, history, and the Earth itself, preserved beneath layers of ice that have endured for millions of years. The hidden lakes beneath the ice are more than frozen refuges. They are archives of time and life, holding clues about the Earth's deep past. Sediments at the bottom of these lakes contain layers deposited over millions of years, preserving chemical signatures, organic material, and traces of microbial activity. By analyzing these deposits, scientists can reconstruct the history of glacial movements, climate shifts, and even the evolution of life in isolated conditions. Each layer is a page in an unbroken narrative, a record of environmental change and biological persistence hidden from the surface world. The biology of these lakes is remarkable in its adaptability. Microbes survive in total darkness, metabolizing minerals and chemical compounds to generate energy. Some rely on sulfur, iron, or methane trapped in sediments, converting these substances into life-sustaining energy in ways unknown on the surface. The extreme conditions have driven evolutionary innovation, producing organisms with unique enzymes, metabolic pathways, and survival strategies. In these lakes, evolution has unfolded on a vastly different timescale, creating ecosystems that are both ancient and highly specialized, demonstrating life's capacity to thrive in isolation. Subglacial lakes also provide insight into the dynamics of ice sheets themselves. Water movement beneath the ice influences glacial flow, ice stability, and even the formation of subglacial channels and ridges. Lakes act as lubricants, allowing massive sheets of ice to slide across bedrock, shaping the landscape over millennia. Understanding these interactions is critical, not only for scientific curiosity, but for predicting the behavior of ice sheets in a warming world. The hidden hydrology beneath glaciers is a key factor in sea level rise and climate modeling, connecting the mysteries of the past with the challenges of the present and future. Technological innovation continues to drive discovery. Robotic submersibles, equipped with sensors and cameras, explore lakes without introducing contaminants. Advanced drilling systems allow sterile access to isolated environments, while satellite and radar imaging reveal the contours and extent of hidden water systems. Each expedition integrates engineering precision with scientific rigor, ensuring that discoveries expand knowledge without compromising the fragile ecosystems below. The technology is an extension of human curiosity, a means to access worlds that were previously unreachable, and a tool for decoding the hidden stories preserved under ice. The polar mysteries are also philosophical. They challenge perceptions of habitability, demonstrating that life can persist without sunlight, under immense pressure, and with minimal energy. The ecosystems beneath the ice are not anomalies. They are proof that life is remarkably adaptable, capable of exploiting niches that humans would consider inhospitable. They expand the boundaries of biology, inviting reflection on what it means to survive, evolve, and endure. Each microbe, each sediment layer, each hidden channel is a testament to resilience, patience, and the ingenuity of life itself. Yet, for all the revelations, the polar regions retain their enigma. Many lakes remain uncharted, and the networks connecting them are only partially understood. The ice conceals as much as it reveals, maintaining a delicate balance between knowledge and mystery. Each new discovery prompts new questions, highlighting the complexity of these hidden systems and the limits of human understanding. The poles are not merely frontiers to be mapped. They are living, dynamic environments, full of surprises, lessons, and untold histories. Exploration of these regions is a dialogue between human ambition and environmental stewardship. Scientists must tread carefully, ensuring that their presence does not disrupt ecosystems that have endured for millions of years. Preservation is as important as discovery, as each lake, sediment layer, and microbial colony represents a unique and irreplaceable record. Ethical exploration is therefore inseparable from scientific progress, underscoring the responsibility that comes with unlocking the secrets of these hidden worlds. As Part 3 concludes, the polar mysteries are revealed not only in the lakes and sediments, but in the intricate relationships between ice, water, and life. They remind us that the planet's most extraordinary stories are often hidden, requiring patience, ingenuity, and respect to uncover. The journey into these frozen frontiers is both scientific and philosophical, revealing resilience, adaptation, and the enduring power of life beneath layers of ice that have persisted for millions of years. The culmination of exploration beneath the ice brings into focus the full magnitude of the polar mysteries. Subglacial lakes, ancient sediments, and microbial life together reveal a world of astonishing complexity and resilience. Here, life has endured in isolation, evolving independently, exploiting chemical energy, and adapting to extreme cold and pressure. The ice that seemed inert is in fact a dynamic partner, shaping these ecosystems, protecting them from disruption, and preserving a narrative that stretches back millions of years. The sediments at the lake floors act as chronicles, recording both geological and biological history. Layers of mineral deposits, organic material, and microbial remnants tell the story of climate shifts, volcanic events, and long-forgotten surface ecosystems. Each stratum provides clues about how ice sheets advanced and retreated, how water circulated beneath the glaciers, and how life responded to changes in chemical and physical conditions. These records are invaluable, offering insight not only into the Earth's past but also into its potential future. By understanding how these isolated systems have persisted, scientists can model responses to environmental changes, anticipate shifts in ice dynamics, and predict the resilience of ecosystems under stress. Life itself is the most striking revelation. Microbes living in eternal darkness are more than survivors. They are innovators. They exploit energy sources that seem foreign to surface ecosystems, metabolizing sulfur, iron, methane, and other compounds to sustain themselves. Their genetic adaptations are unprecedented, representing evolutionary experiments that occurred far from sunlight and surface life. These organisms challenge assumptions about the requirements for life, showing that the fundamental principles of survival are universal, capable of transcending environments previously deemed uninhabitable. The lakes beneath the ice are living laboratories, demonstrating how life adapts, thrives, and persists when removed from the familiar rhythms of the surface world. Technological ingenuity has allowed humanity to access these hidden frontiers without compromising their integrity. Sterile drilling, autonomous underwater vehicles, and sophisticated sensors enable scientists to study lakes, sediments, and microbial life with unprecedented precision. Each expedition balances discovery with preservation, minimizing impact while maximizing insight. Through this careful interplay, the polar regions reveal not only the history of life on Earth, but also a blueprint for responsible exploration, showing that scientific curiosity can coexist with environmental stewardship. The polar mysteries extend beyond Earth. The lessons learned from subglacial ecosystems inform our search for extraterrestrial life. Icy moons and planets may harbor subsurface oceans, shielded from sunlight, yet capable of supporting life. Microbial survival strategies beneath the ice provide analogs for what might exist elsewhere in the cosmos, offering hope that life is not limited to habitable zones defined by surface conditions. Earth's hidden lakes serve as guides, demonstrating that resilience, adaptation, and ingenuity can allow life to flourish even in the most extreme isolation. Yet, despite the scientific advances, the poles retain an aura of enigma. Many lakes remain undiscovered. Channels and hydrological connections are only partially mapped, and microbial communities remain largely unstudied. Each new discovery reveals the complexity of these systems and deepens our appreciation for the planet's hidden wonders. The ice conceals as much as it reveals, preserving secrets that challenge our understanding and inviting continual exploration. The polar frontiers are at once accessible and remote, known and unknowable, a reminder that Earth still holds mysteries that defy human expectation. Human engagement with these regions carries both privilege and responsibility. The ecosystems beneath the ice are fragile, having endured for millions of years. Exploration must prioritize preservation, preventing contamination and ensuring that these ancient worlds remain intact for future generations. Ethical stewardship is inseparable from scientific inquiry, highlighting the delicate balance between curiosity, understanding, and protection. These are lessons not only for the poles, but for humanity's broader relationship with the natural world. As Chapter 5 concludes, the polar mysteries emerge in full clarity. They are tales of endurance, adaptation, and innovation, chronicled in ice, water, and life. Subglacial lakes, ancient sediments, and resilient microbes illustrate the extraordinary capacity of life to persist under conditions once thought uninhabitable. The hidden frontiers beneath the ice are both archives and laboratories, preserving the past while illuminating the possibilities for the future. Unlocking their secrets is a journey into the very essence of survival, resilience, and the boundless ingenuity of life on Earth, and perhaps beyond. The hidden world beneath the ice whispers stories older than human memory. Subglacial lakes, isolated for millions of years, are living archives of evolution, chemical processes, and climatic history. In these dark, pressurized waters, life persists where none was thought possible, revealing resilience, adaptation, and the silent poetry of existence. The ice above is more than a barrier. It is a protective veil, preserving a dynamic system that balances water, sediment, and life in a delicate equilibrium. Each lake holds a unique narrative, shaped by chemical composition, pressure, and the subtle flow of water through kilometers of ice. The sediments at their floors are like ancient scrolls, recording shifts in mineral content, temperature, and microbial activity. Microbes interact with these sediments, metabolizing nutrients and influencing the chemical environment. Their survival strategies are extraordinary, revealing metabolic pathways that challenge conventional biology and illustrate the adaptability of life in isolation. These lakes are not lifeless voids. They are thriving, intricate ecosystems, shaped over eons and teeming with silent activity. The ice itself contributes to this hidden world. Pressure from kilometers of ice maintains liquid water beneath the surface, while its slow movement sculpts channels, ridges, and basins that direct water flow. Geothermal heat from the Earth prevents freezing, allowing these lakes to remain liquid despite sub-zero temperatures. Ice cores extracted above these lakes carry chemical and physical clues about the history of the surrounding environment, from ancient volcanic eruptions to shifts in climate. Every layer of ice is a storyteller, connecting the past to the present and bridging the visible and hidden worlds. Technological innovation allows humanity to witness this concealed domain. Sterile drilling ensures that ecosystems remain untouched, while robotic submersibles navigate icy waters to collect chemical and biological samples. Satellite and radar imaging reveal hidden channels in topography, mapping the intricate relationships between ice, water, and life. Through this fusion of technology and observation, the polar frontiers unfold, showing not only the resilience of life, but also the interconnectedness of the Earth system. These lakes also provide insight into broader planetary processes. The chemical interactions within sediments, the circulation of water beneath ice, and the metabolic activity of microbes contribute to nutrient cycling, greenhouse gas dynamics, and energy flow. They are microcosms reflecting principles that operate on planetary scales, demonstrating how even isolated systems can influence climate, chemistry, and life over vast temporal spans. Each lake is a laboratory where the rules of chemistry and biology are both preserved and tested under extreme conditions. The life forms inhabiting these lakes are remarkable in their diversity. Microbes have evolved independently in each isolated environment, developing unique enzymes, metabolic pathways, and survival strategies. Some rely on sulfur or iron oxidation, while others exploit gases like methane or hydrogen dissolved in sediments. These adaptations show that life is not bound to sunlight, surface ecosystems, or conventional energy sources. It thrives in darkness, pressure, and scarcity, offering insight into the universal potential of survival. Beyond biology, these hidden ecosystems serve as historical records. Sediments preserve evidence of ice sheet movements, ancient climates, and geological events. Traces of volcanic eruptions, dust from distant continents, and microscopic particles offer snapshots of environmental conditions that occurred hundreds of thousands, even millions of years ago. By studying these records, scientists reconstruct Earth's history, uncover patterns of climate change, and gain insight into the forces that shaped both surface and subsurface environments. The interplay between ice, water, and life is a narrative of persistence. Each element influences the others. Ice maintains pressure and temperature, water circulates nutrients and energy, and life shapes the chemical environment. This interconnection is subtle yet profound, revealing a system where change is gradual, evolution is deliberate, and survival is measured in millennia. In these hidden worlds, the echoes of the past resonate in every droplet of water, every layer of sediment, and every microbial cell. Beneath the ice, time flows differently. In subglacial lakes, years and centuries pass silently, recorded in sediments, chemical gradients, and the slow metabolism of life. Microbes in these hidden waters exist in a rhythm dictated not by sunlight, but by chemical energy and the stability of their environment. Their existence is a testament to patience and adaptation, demonstrating that life can thrive without urgency, evolving slowly, deliberately, over millennia. In this quiet persistence, the hidden world preserves lessons about resilience, endurance, and the ingenuity of nature. The chemical composition of these lakes shapes the ecosystems within. Variations in salinity, mineral content, and dissolved gases create niches for specialized life forms, each uniquely adapted to its microenvironment. Some microbes metabolize iron or sulfur, others utilize methane trapped in sediments. Energy flows through these systems in subtle, highly efficient cycles, allowing life to survive in conditions that would seem impossible on the surface. The chemical makeup of each lake is both a constraint and an opportunity, guiding evolution in unexpected directions and revealing strategies of survival that challenge our understanding of biology. Pressure from the overlying ice influences more than just water flow. It molds the very fabric of the ecosystems below. Kilometers of ice exert immense weight, maintaining liquid water despite extreme cold, while slow glacial movement sculpts channels and basins that direct nutrient circulation. This combination of stability and slow dynamism ensures that life has a stable yet flexible environment in which to evolve. The ice is at once protective and directive, shaping ecosystems without interfering with their delicate balances, allowing life to persist and adapt over geological timescales. Sediments at the lake floors act as both archives and energy sources. Layers of mineral deposits, organic matter, and microbial remnants chronicle the passage of time while supplying nutrients to the communities above. These sediments reveal past events, from glacial advances to volcanic ash deposits, creating a continuous record of Earth's hidden history. Microbes interact with these layers, recycling nutrients, influencing chemical gradients, and sustaining life in isolation. Each interaction is subtle but vital, a reminder that survival in extreme environments relies on both individual adaptation and ecosystem interdependence. The isolation of these lakes also drives evolutionary innovation. Cut off from sunlight and external microbial populations, organisms develop unique genetic traits, metabolic pathways, and survival strategies. Some genes discovered in these microbes have no known equivalents on the surface, encoding enzymes capable of functioning under extreme pressure and low temperatures. These adaptations highlight the creative potential of evolution when constrained by extreme conditions, revealing that life can find solutions in isolation that might never appear in more conventional environments. Technological exploration of these hidden worlds continues to push boundaries. Sterile drilling techniques allow access to lakes without introducing contaminants, while robotic submersibles navigate their depths, capturing chemical, biological, and physical data. Satellite imagery and radar mapping reveal the contours of lakes and channels beneath kilometers of ice. Each technological advance provides a new lens into the hidden world, allowing humanity to observe, understand, and respect ecosystems that have endured for millions of years. The more we explore, the more intricate and interconnected these systems appear. These hidden ecosystems offer insight into life beyond Earth. Icy moons such as Europa and Enceladus may harbor subsurface oceans, shielded from sunlight, yet capable of sustaining microbial life. The adaptations observed in Earth's subglacial lakes provide models for what life might look like elsewhere, showing that survival is possible in isolation, under extreme pressure, and without conventional energy sources. The polar frontiers thus become guides for astrobiology, demonstrating that the potential for life extends far beyond our familiar planet. In the echoes of these hidden worlds, we find both knowledge and wonder. The lakes beneath the ice are not simply scientific curiosities. They are living narratives, preserving the interplay of chemistry, geology, and biology across millions of years. They teach lessons about patience, resilience, and adaptation, offering glimpses of how life thrives in silence, in darkness, and under pressure. Through them, we begin to understand the profound complexity and interconnectedness of Earth's hidden systems. The hidden world beneath the ice is a study in contrasts, isolation and interconnection, stillness and slow motion, darkness and life. Each subglacial lake is unique, shaped by its chemical composition, pressure, and surrounding ice. Yet together, these lakes form an interconnected network, linked by subtle water flows, channels, and melt pathways that span kilometers beneath the frozen surface. This hidden hydrology not only sustains life, but also preserves a record of Earth's past, storing chemical and biological signals that trace the planet's evolution over millions of years. Within these waters, life is both fragile and tenacious. Microbial communities, evolved in isolation, survive with minimal energy, metabolizing minerals and gases locked in sediments. Some microbes thrive on iron, others on sulfur, methane, or hydrogen, illustrating the versatility of life under extreme constraints. Their survival strategies are lessons in efficiency, resilience, and adaptability, revealing the unexpected ways life can persist when traditional resources are absent. Studying these organisms expands our understanding of biology, showing that life is not bound to sunlight, warmth, or abundance. It is boundless in its capacity to adapt. The ice above these lakes plays a dual role, protector and sculptor. The immense pressure it exerts maintains liquid water beneath freezing temperatures, while slow glacial movements shape channels, ridges, and basins that direct water and nutrient flow. This constant yet gradual movement ensures that ecosystems remain dynamic, allowing nutrients to circulate, sediments to accumulate, and microbial communities to thrive. The ice is both a silent guardian and an active participant in the ecological and chemical processes occurring below, maintaining equilibrium over geological timescales. Sediments at the lake floors are invaluable archives of history. Layers of minerals, organic matter, and microbial remnants chronicle environmental events such as glacial advances, volcanic eruptions, and atmospheric changes. By examining these deposits, scientists reconstruct past climates, track shifts in ice sheet dynamics, and uncover evidence of ancient life. The sediments are living records, both preserving and sustaining the ecosystems above them, demonstrating the intimate connection between geology and biology in these hidden worlds. Technological advancements have allowed scientists to probe these isolated environments with unprecedented precision. Sterile drilling ensures that lakes remain uncontaminated, while robotic probes navigate subglacial waters, capturing detailed measurements of chemistry, temperature, and microbial activity. Satellite imagery and radar mapping reveal the contours of lakes and hidden channels, showing how water moves beneath kilometers of ice. Each tool expands our understanding of these ecosystems, revealing complexity, interconnection, and a subtle dynamism previously invisible to human eyes. The ecosystems in these lakes are also mirrors for the search for extraterrestrial life. Icy moons such as Europa or Enceladus may harbor subsurface oceans under kilometers of ice, with life that relies on chemical energy rather than sunlight. The metabolic adaptations of Earth's subglacial microbes provide models for potential extraterrestrial survival, showing that life can thrive in isolation, darkness, and extreme pressure. These hidden lakes are both a window into our own planet's history and a guide for understanding life beyond Earth, bridging planetary science and astrobiology. Exploration of these worlds is not without responsibility. The ecosystems have remained pristine for millions of years, and even minor contamination could irreversibly alter them. Scientists must balance curiosity with stewardship, ensuring that discovery does not come at the cost of destruction. Ethical exploration is inseparable from scientific insight, reinforcing the principle that humanity must tread lightly in environments older and more enduring than our species. In observing these hidden ecosystems, we witness the delicate harmony of Earth's systems. Ice, water, sediment, and life are interdependent, each influencing the other in subtle yet profound ways. The lakes beneath the ice are living narratives of resilience, adaptation, and persistence. They preserve history, sustain life, and challenge our understanding of the limits of survival. Through them, we glimpse the intricate and enduring complexity of our planet, a hidden world echoing with lessons millions of years in the making. The final revelations of the hidden polar world lie in the interdependence of its elements: ice, water, sediments, and life. Each subglacial lake is a self-contained ecosystem, yet collectively they form a vast interconnected network that preserves Earth's history and sustains life in extreme isolation. The ice above shields these lakes from environmental fluctuations, while subtle water flows circulate nutrients, allowing life to persist. In this intricate balance, every molecule of water, every sediment layer, and every microbial cell contributes to a story millions of years in the making. Sediment cores extracted from these lakes reveal the rhythms of the Earth itself. Layers of minerals, volcanic ash, and organic matter chronicle periods of glacial advance and retreat, climate change, and even distant volcanic eruptions. Microbial fossils embedded in the sediments tell of life persisting in complete isolation, offering glimpses into evolution unconstrained by surface ecosystems. These layers form a timeline that is both biological and geological, a record of processes invisible to human eyes, yet enduring in their precision. Through careful analysis, scientists reconstruct not only the history of these hidden systems, but also broader patterns of Earth's environmental evolution. The life within these lakes is extraordinary. Microbes metabolize chemicals trapped in sediments, using iron, sulfur, or methane as energy sources. Their genetic adaptations are unique, encoding enzymes and metabolic pathways capable of functioning under extreme pressure, near freezing temperatures, and complete darkness. These survival strategies illuminate the astonishing versatility of life and its capacity to exploit conditions previously thought uninhabitable. Studying these organisms challenges our assumptions about the limits of biology, offering insight into how life might endure in environments far beyond Earth. Technological ingenuity has allowed humans to access and study these fragile ecosystems without causing harm. Sterile drilling prevents contamination, while robotic probes navigate the depths, measuring chemical properties, recording imagery, and sampling sediments. Satellite and radar mapping reveal the contours of lakes, hidden channels, and subglacial rivers. These tools uncover the hidden architecture of polar ecosystems, providing a detailed understanding of how ice, water, and life interact. Each discovery illuminates not only the physical and biological processes at play, but also the delicate balance that has preserved these systems for millions of years. The knowledge gained from these hidden lakes extends beyond Earth. Icy moons such as Europa and Enceladus may harbor oceans beneath kilometers of ice. The metabolic strategies observed in subglacial microbes provide a template for imagining how life might exist in these alien oceans. The polar frontiers of our planet thus serve as a natural laboratory, bridging the study of Earth with the search for life elsewhere in the cosmos. They remind us that the potential for life is not limited to familiar conditions, and that survival is a universal force, adaptable to environments both extreme and isolated. Yet the polar mysteries are not fully revealed. Many lakes remain uncharted, their waters unexplored, and their ecosystems unstudied. The ice conceals channels, basins, and habitats that may harbor life forms and chemical processes unknown to science. Each new discovery raises questions as quickly as it answers them, emphasizing that exploration is both a journey of knowledge and a dialogue with mystery. The polar regions are dynamic, complex, and enduring, a reminder that Earth's most extraordinary stories often lie hidden beneath the surface. Ethical stewardship is central to exploration. The ecosystems beneath the ice have persisted for millions of years, and even minor disturbances could irreversibly alter them. Scientists approach these lakes with reverence, ensuring that discovery is coupled with protection. This balance between curiosity and responsibility underscores a universal truth, that knowledge carries obligation. To explore is to respect the fragility and resilience of life, and to honor the histories preserved beneath kilometers of ice. As Chapter 6 concludes, the echoes of this hidden world resonate clearly. Ice, water, sediments, and life form a complex, interconnected system that preserves the past, sustains life, and hints at possibilities beyond Earth. These subglacial lakes are more than scientific curiosities. They are living archives, laboratories of evolution, and testaments to resilience. In their darkness and isolation, they illuminate the extraordinary capacity of life to endure, adapt, and thrive. The hidden polar world teaches us that even in silence and stillness, the Earth speaks, echoing lessons millions of years in the making.